Alright, are you ready for me to read it?
Yes.
A baseball rolls off a .70-meter high desk and strikes the floor at .25 meters away from the base of the desk. And how fast is the ball rolling is the question.
Okay, great. So are you familiar with some of these equations, like the final velocity equals the initial velocity? Your book uses delta x, right?
Yeah.
Okay, great. So this is delta x. Okay, so the question in this problem is how fast is the ball rolling, right? So we're going to call it the horizontal velocity is the question. Is that true? Did she say before it left the table or when it hit the ground?
It doesn't say. A ball rolls off .70 meters high off the desk, strikes the floor at .25 meters away from the base of the desk. How fast is the ball rolling?
How fast was the ball rolling? And she doesn't say before it goes off the desk, but I think because she's saying how fast was the ball rolling, I think she's asking for the velocity of the ball before it rolls off the edge of the desk. Because I think if she was asking for how fast it was going before it hit the ground, she would say something like, how fast is the ball going when it strikes the ground? Like she would be more specific. So I think she's talking about right here as it rolls off. Now, check out as the ball rolls off. You know this ball is rolling horizontally across the desk, right?
Yeah.
Right before it goes off the edge, does it make sense to you that it doesn't yet have a vertical velocity? Like right now, before it goes off the edge, it's only horizontal.
Yeah, that makes sense.
Okay, so initially the vertical velocity, I'm going to call it V, like V-ver, or later I'll just call it VV for vertical velocity. Initially equals 0 meters per second. So this vertically at least is 0 at first. But she's wondering about the horizontal as it's going off the edge of the desk. So in order to solve these problems, the trick or the thing that makes it easy to solve these problems is to completely separate the horizontal information from the vertical information. Has she taught you to do that yet?
No.
So you're going to make a table with all of these projectile motion problems and all these free fall problems. The ball or the football or whatever it is, or the airplane, I mean, it's actually not an airplane because an airplane hopefully is not in free fall. But if a package is dropped from an airplane, then that would be free fall. In all of these problems, they're actually going to be flying through the air horizontally and vertically, sort of like over and down, like this ball is going over and down off the table. So even though the motion is both horizontal and vertical at the same time, what you want to do mathematically is separate the horizontal from the vertical so that whenever you plug numbers into an equation, you're either going to be plugging in horizontal numbers into an equation or vertical numbers into an equation, but you're trying never to mix the two.
Okay.
So I'll show you how to do that. The best way to get your mind to think of them as separate is to make a table and be like, okay, I have to list my horizontal information and I have to list my vertical information. And the types of information I mean are velocity, distance, acceleration, and time. Stuff like that. Okay. Are you good so far? All right. Now, velocity horizontally, that's actually what we need. So I'm just going to kind of put a box right here and say, hey, that's going to be our answer. Now, do you know a horizontal distance? Look at our drawing.
0.25.
Very good. 0.25 is the horizontal distance. So at least we know that. Trick question. Is there a horizontal acceleration? Or do you know the acceleration horizontally?
Not that I know.
Exactly. Good answer. There is no gravity pulling it faster and faster horizontally. And in high school physics, at least, we're going to neglect air resistance, which means it's not going to slow down because of air resistance. So we are going to say horizontally that the acceleration is 0, and you don't even really, from now on, have to list acceleration on the horizontal side.
Okay.
Until college, when they say, oh, you have to figure out the air resistance. Now, time horizontally was not given to us, so we'll just leave that blank for right now because we don't know it yet. But let's try to list some things vertically. Vertically, do you agree that there's some acceleration going on?
Yeah. Well, there's gravity.
Exactly. Gravity is causing acceleration. So do you remember what the acceleration due to gravity is? Has she taught you the number yet?
-9.81.
Yeah, very good. So acceleration due to gravity is little g, which is negative 9.81 meters per second squared vertically. So we know that. Do we know the vertical distance?
0.70 meters.
I like that. Do we know, okay, because there's acceleration vertically and the velocity is going to be speeding up, does it make sense to you that we're going to have an initial velocity and we're going to have a final velocity?
Yeah.
Okay, great. So initially, what did we already say about that vertical initial velocity?
It is 0.
Yeah, because at first, before it falls, vertically, it didn't have any velocity. It was just rolling off horizontally at first. So at first, the vertical is 0. But the final velocity is going to be the velocity down here right before it hits the ground. Now, she didn't ask you to solve for that, but sometimes they will.
Okay.
And some students are like, well, when it hits the ground, its final velocity is 0 because it's going to stop. And the teachers are like, no, I mean the final velocity right before it hits the ground. So just, be careful that you don't think about after it bounces or something like that. And so we're going to leave the final velocity blank, and then the time, we also don't know because she didn't tell it to us. But so far we've filled in on our table everything that we know. And do you see how we did a nice job of separating the horizontal and the vertical?
Uh-huh.
This is going to really help when we plug into equations. Now, the 3 equations at the top, do you see how they all include acceleration? These are actually not going to be used horizontally because horizontally there isn't any acceleration. So these equations would sort of be useless. So these equations are actually going to be just your vertical equations, which is nice because that makes it simple. You can only use these for your vertical free fall. Now, the other thing that's really cool is that horizontally, there's only one equation you get to use. So horizontally is like very simple. Horizontally, all you get to use is velocity is distance over time. And because there's no acceleration horizontally, the velocity horizontally is constant.
Okay.
So whatever velocity it has horizontally when it rolls off, it keeps on having that horizontal velocity the whole time it's going. So we've separated our information horizontally and vertically, and we've also separated our equations horizontally and vertically. So now we're just ready to plug in. Since she's asking for the initial horizontal velocity, do we have enough information to solve right now using the blue box horizontal equation? Do we know? I think we know the horizontal distance, but do we know the time for the fall?
No. So we can move it around.
Yeah, right. How do you want to move that around?
Well, we know D.
Good. Check.
But we don't really know T, and we don't really know V.
Right. So there are 2 unknowns, which means when you have 2 unknowns, you actually need 2 equations to combine the 2 equations. But since we don't have 2 horizontal equations, we're going to have to steal T from the vertical side. Now, we separated the horizontal and the vertical information, but do you agree that when this ball falls, that the time it's falling vertically is the same time that it's moving horizontally?
Yeah.
Okay, so the one thing that you actually get to put on both sides of this equation, the one thing that they share is the time for the fall.
Okay.
And so what we're going to say is the time will kind of have that crisscross over on both sides of the equation. So what normally happens in most of these problems is that time is what you don't know, and time is sort of like the most important thing in these problems to figure out, because once you figure out how much time it took for the thing to fall, all of a sudden all the equations become easy because you're just plugging things in. So
okay.
I like to say that figuring out the time, see if I can draw a key.
Oh.
Sort of?
Yeah.
So I like to say that time is the key that unlocks these problems. Because once you find the time, you're good to go. Everything all of a sudden gets easy. So since the time is the same on the horizontal and the vertical side, I know that we need it to solve up here in the top right-hand corner for our velocity. But maybe the vertical side could give us a clue about the time. So let's work with all of these vertical equations and see if we can figure out time from those equations. And this is how most of the problems are going to work. You're going to have to work a vertical equation to get the time and then use it in the horizontal equation, or vice versa.
Okay.
So look at these equations and tell me if there's any of them where we know enough information to actually get the time.
I'm not seeing a whole lot. Well,
Yeah,
you can do
going.
the first one.
Okay, the first one. So do we know final velocity before it hits the ground?
No.
We don't. So I'm going to put a frowny face. We can't use the first one to find time. What about the third one? Do we know the vertical distance?
Yes.
Okay. Do we know the initial vertical velocity?
Yes.
Good. We know this and we know this. And do we know the vertical acceleration?
Yes.
We got it all. We can do the third one and get the time. Should we do it?
Sure.
Okay. So I'm going to rewrite the equation right over here. Okay. What is the vertical distance? And I want you to be careful before you, think about it a little bit longer before you say 0.70 meters. What is special about this vertical distance? Think about direction.
Not negative.
Good. It is. Yeah, it's written. They're going to give you in the problem. They're not going to tell you to make it negative. They're just going to say, oh, the table is 0.70 meters tall or high, right? They're seeing if you know, because the ball's falling downward, they're going to test you to see if you know to make your distance in the equation, not in the drawing, but in the equation, to make it negative. And tell me again why we need to make it negative.
Because it's falling.
Yeah, it's falling down. And we like to say down is negative and up is positive. So that's the way we do it in physics. So the negative 0.70 is our distance. Be very careful with that. What's our initial? Remember, this is all vertical. We're plugging only vertical information in. You can't mix horizontal and vertical. So everything we're going to do here is vertical. What's our initial vertical velocity?
0.
Perfect. What's our acceleration vertically?
Negative 9.81 meters per second.
Good. Yeah, meters per second squared. I love the fact that you made it negative. And then the t is what we're looking for. So we're starting to feel good. Aren't you starting to feel good? Like we're getting there?
Yeah.
All right. So I'm going to take 0.5 times negative 9.81. And it's like 4.905. So it's like negative 0.70 equals negative 4.905 t squared. So then I'm going to do 0.7 divided by that. So t squared I get is 0.1427. And so then I'll take the square root of that. Okay, so I get for our time 0.37777. It's fun to write a bunch of sevens in a row. All right, and after that last 7 I wrote, there's a 1, so it's not exactly repeating. All right, so 0.37777 seconds is our time for the fall. We have just unlocked the problem. Once you find the time, you've unlocked it, you found the key. So now we know the time for the fall. Do you think the horizontal time for the fall is the same as the vertical time for the fall?
It is.
I know, I do. I think so too. So I'm going to go over here to my chart on the left, and I'm going to say 0.3. How many significant figures? It's 2, right?
Yeah.
0.38 for the time. Oh, and we get to write it down here too. 0.38 seconds. And for seconds, have I already told you to always do SEC?
Yeah, so it doesn't look like a 5.
Yeah, so it doesn't look like a 5, because otherwise it would look like 0.385. All right, so we got 0.38 seconds for the time. Yay, we figured out the time. Now we can take that and we can do like a horizontal equation. And what's our only horizontal equation for free fall?
V equals D over T.
Perfect. Do we know the V?
Velocity is, no, we don't know that.
Okay, we're looking for it. Do we know the D horizontally?
Is 0.25 meters.
What's our time again?
0.38 seconds.
All right, let's calculate this velocity distance over time. So 0.25 divided by that 0.37 number. Okay, so I get 0.66 meters per second for the horizontal velocity. So I'm going to put it up here in the box if I can fit it, 0.66, and I'm going to squeeze the meters per second. What do you think so far?
Looks good. Here, you're not gonna switch pages, are you? Because I'm gonna write this down for a little bit. Give me like 2 seconds. You can keep talking.
Sure. All right. So we were careful to make the downward distance when something's falling. We made sure that was negative. We made sure our acceleration due to gravity was negative because that's pulling downward. We found the time using the vertical information. And then that time we switched over to the horizontal side. We were able to plug in that time to get the horizontal velocity. And we solved the problem. We kept the horizontal and the vertical information separate except for the time. And we kept the horizontal and the vertical equations separate. And we were careful to plug vertical information into vertical equations and horizontal information into horizontal equations.
Okay.
So I've got the cat and the mouse on the table. The mouse goes out of the way and the cat flies off. And it's 2.2 meters away that the cat lands. So the horizontal distance for the cat is 2.2 meters. Okay?
When the cat slid off the table, what was its speed? So this is basically the same thing. But I don't know if the cat's going horizontally or vertically.
Yeah, when the cat slid off the table, probably horizontally.
Okay.
Yeah, and then started to fall after it slipped off the table. So the exact same process we just did.
This kind of sounds like the same thing too. A pelican flying along a horizontal path drops a fish from a height of 4 meters.
Mm-hmm.
The fish travels 8 meters horizontally before it hits the water. What is the pelican's speed? And then another pelican is if the pelican in question 3 was traveling at the same speed but was only 2.7 above the water, how far would the fish travel before hitting the water?
Okay, great. So here's what I'm going to do for that one. So I'm going to pause the recorder just for a second. The horizontal velocity of the pelican before dropping that fish, and it turned out to be 8.9 or 8.86 meters per second. And so we needed that information because the next problem is relying on this exact horizontal velocity. But now the pelican is going to be something like, what is it, 2.7 meters high?
Yeah.
Okay, so I'm going to turn the page as long as we remember that 8.9 meters per second is the pelican's velocity. And we're going to say 8.9 meters per second is, oh, you know what would be fun? To try to draw the pelican. So watch this.
Hey, that's pretty good.
All right, so the body, let's see if we can see the body. And what the wing? I'm going to do some little feet like this. Does he have a tail? Well, the wing is huge. I drew the wing way too big, but that's his wing right there. Oh, he needs an eyeball.
Oh, there we go.
All right, so it's kind of a tail, and his wing is huge. No big deal. All right, so I am going to make him fly 8.9 meters per second, but now the new problem says he's only 2.7 meters tall, or high up off the water.
Okay.
So he's dropping the fish now. So now the teacher's asking, how far does the fish go horizontally? I'm going to make him a little pink fish. So now we've got to list our horizontal and our vertical information, see what we know and what we don't know. Horizontally, the distance we don't know, we're going to leave that, like we're expecting to find it. What else do we know?
Acceleration.
Good.
Oh, wait, there's no horizontal. There's no horizontal.
Good.
We know, oh no, we don't know distance. Time, we don't know time. Velocity is 8.7 meters a second.
Yeah, 8.9 maybe. Mm-hmm.
That's the only thing we know.
Horizontally, right, that's the only thing we know. we might have to unlock the problem using time on the vertical side.
Okay.
All right. What do you know vertically?
2.7.
Okay, good. So the distance vertically is 2.7. What is special about the vertical distance?
It's positive?
I think it's negative. Is the fish falling down or going up?
It's going down. It's going down.
Yeah, so I think we should make it negative because he's falling down. Okay, what else do we know vertically?
Acceleration?
Okay, what is that?
Negative 9.81 meters a second squared.
I like it. Do we know anything else vertically? Like, do we know either an initial vertical velocity or a final vertical velocity?
Well, isn't initial always 0?
It is in these problems so far because initially the bird was only flying horizontally.
Okay.
Later, when we kick a football and you kick it and it's going up and over, the initial vertical velocity won't be 0 because it's going like up and over. But in these problems, when before the thing drops, it's just going horizontally, then yes, these are going to be sort of like vertically dropped from rest, but not exactly from rest because all it had was horizontal velocity. All right, we don't know final velocity, but we've got a lot of good information. And then the time is going to be the key. And we'll just crisscross there with the time on both sides because as soon as it stops, as soon as the fish lands and stops falling horizontally, it also stops falling vertically.
Okay.
All right. Do we have enough information? I'm going to list these nice equations. And I want you to think about memorizing these unless your teacher says that she's going to give them to you at the top of every test. Did she tell you whether you have to memorize them?
No.
Okay, so ask her, say, hey, do I have to memorize these equations or are you going to give them to us on the test?
Okay.
All right. So are these equations vertical or horizontal?
Vertical.
Good. We're going to use these vertically.
There's only one horizontal equation.
Nice. What is it?
V equals E over T?
V over T, right. And you can remember that because your speed when you're in the car is miles per hour. And you know miles is distance and hour is time. So it's always like miles per hour. Okay, that's distance over time. Okay. So we've got our vertical and we've got our horizontal. Look at your vertical equations. Do we have enough information to use one of those to solve and get time, which is the key that unlocks everything?
We have initial to we can use the second one. Oh wait, but we need time, so we have to use the third one.
Good, because we're looking for time. The second one we might be able to use, but hey, it doesn't give us time. All right, so because we are looking for this horizontal distance, so we want to get to that horizontal equation if we can. So let's do that third equation that you suggested, and I'm going to switch back to this pretty blue. So I'm going to go distance equals VIT. Oh, it's a lighter blue. Plus 1/2 AT squared. So help me plug in something. Do we know D?
We have VI is 0.
Okay, good.
And then time we don't know is T plus 1/2 negative 9.81 meters a second squared times T again, which we don't know.
Okay, and T is going to be squared. And what is the D on here?
Well, we don't know that.
I think we do know the D vertically.
Oh, vertically?
Yeah, look. Yeah, negative 2.7, that's right. That's why we want to make sure that we keep the vertical and the horizontal separate, because vertically we do know the distance, even if horizontally we don't.
Okay.
Are we good with plugging in and doing the algebra now?
Yep.
Okay. I'm going to take the negative 2.7 and divide by negative 4.905, which is half of 9.81. So I get 0.55 equals T squared. So I'm going to take the square root of both of those guys. I get 0.7419.
Yeah, I got a small number.
Okay, 0.74 seconds.
Wait, how if you take the square root, it's bigger than...
Yes, exactly. You know what's really wild? For every number, when you square it, it gets bigger, right? Every single number, except for the decimals between 0 and 1, and 0 and -1. It's
Really?
like right between 0 and 1, like if something's less than 1, and it's like point something, when you square it, it gets small.
That's weird.
I know. It kind of blows my mind. It blew my mind when I realized it. Yeah. Because you're actually multiplying it by a fraction. You're multiplying a fraction by a fraction, which can make it smaller.
Okay.
So, yes, when you take the square root of a decimal like this, it's less than 1, the number actually gets bigger.
So now we have the time for the horizontal also.
Yes,
So
we
now
do.
we can fill in. We don't have the d, but we have the velocity, and we have the time.
Very nice. So the d we need, and the time is 0.74. And your time should always turn out to be positive. If it turns out negative, then something's wrong with the equation. So I get a d of 6.6 meters. Is that what you got?
Yep.
Okay, so we can fill it in up here and say 6.6 meters. And that is what we solved for, and that's what they asked for.
All right, perfect.